Alright, I hope everyone's doing alright today. Staying warm and everything else. Today we're going to be looking at section 9.2, which is on series and convergence. Alright. So we start off with the definition of infinite series. And infinite series is written as a sum of a sub n, as n goes from 0 to infinity, or we could use 0 or 1 here. I prefer to use 0, the book uses 1. Okay. And the idea is that we're adding together all these terms, a0 plus a1 plus a2 plus a3, all the way up to a infinity, which we never technically get to. But we're just adding all these terms together. It's like and it's a lot like a sequence, except in sequence it's just a list of terms, really. In an infinite series, we take that list of terms from the sequence and add all the terms together. And that's really what it amounts to. So if we had, for instance, let's see, we have the sum n equals 0 to infinity of 2 to the n. This would be 1 for n equals 0. N equals 1 would give us a value of 2. N equals 2. 2 squared would give us 4. N equals 3 would give us 8. N equals 4 would give us 16. And so on. So that eventually the numbers are getting larger and larger, and it looks like they'll continue to grow without stopping. Okay. So that's one example of an infinite series. We also have the let's see if I can find it. We have the concept of what we call a telescoping series, which is a specific type of infinite series. And that would be something like this. Sum n equals, and we'll start at 1 this time. We have 1 over n minus 1 over n plus 1. And the reason we start at 1 is because if we actually plugged in 0, 1 over 0 is undefined. So we cannot include n equals 0 as part of the series because it results in an undefined value. So telescoping series, if we look at the first couple of terms here, n equals 1, you get 1 minus 1 over 2. N equals 2 would give us 1 over 2 minus 1 over 3. N equals 3 would be 1 over 3 minus 1 over 4. Excuse me. And then n equals 4 would give us 1 over 4 minus 1 over 5. Now what we see happens here, this is why we call it telescoping, is that a lot of our middle terms are going to cancel each other out. Like minus 1/2 and plus 1/2, that's going to cancel each other out. Minus 1/3 plus 1/3, that's going to cancel each other out. Minus 1/4 plus 1/4, that's going to cancel each other out. So we keep going until we get to the nth term. Nth term is 1 over n minus 1 over n plus 1. Now we know, based on the pattern that we see happening here, eventually 1/5 is going to be cancelled out by the following term. And this, if this is the nth term, we know 1 over n is going to be cancelled out by the previous term. You know, whatever that previous term happens to be. Now this concept that we're looking at right here is what we call a partial sum. Sorry, I'm having some logistical issues with my textbook. This concept is a partial sum, and the idea is that we look at the sum of the first n terms, and we call it S sub n. This is a partial sum. The reason it's called a partial sum is because it's only a sum of part of the series. It's only the first however many terms that we look at. And so we notice with all of these adding together, all of these terms will cancel, 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 cancel. And then this one will be canceled by whatever term comes before that. So only the 1 and the minus 1 over n plus 1 is left over. So S sub n is equal to 1 minus 1 over n plus 1. This really only applies in telescoping series. I mean, we can use partial sums anywhere, don't get me wrong. But this kind of thing only really applies in what's called a telescoping series, where different terms are canceling each other out. It may not always be like these two right here. It may be these two cancel, these two cancel, these two cancel, and so on. It may be a little bit wider of a interval that we're looking at, but the principle is still the same, that terms that are subtracted in part of one value are then added in a later value, or vice versa. And that's what makes a telescoping series. What makes the partial sum especially useful here is that we can now determine the convergence or divergence of the series based on that. It's not always possible, but in this case it happens to be possible. This is the sum of the first n terms. What happens if we let n go to infinity? And that's how there's one way that we can determine convergence and divergence. Now we're looking at convergence and divergence using partial sums. So we define Sn, the nth partial sum, Sn is equal to A1 plus A2 plus A3 all the way up to An. Basically, sum of the first n terms. And so we add up to the first n terms. And so it turns out that the limit of the series is equivalent to the limit as n goes to infinity of S sub n. So if S sub n diverges, then the series diverges. Okay. If S sub n converges, then the series converges to that value. Now what that means in this convergence is whatever value S sub n converges to, then the series will converge to that same value. Okay. So essentially what we're saying is that if we say we can say that the sum of a sub n from n equals 1 to infinity is equal to the limit as n goes to infinity of S sub n. Now, this one really wasn't included in the book. I think they were trying to not get too technical at this point in the discussion. But this is essentially what is being said. If we want to find the actual value of the sum, like what happens when we add all these numbers together, then if we can establish a partial sum S sub n and take its limit as n goes to infinity, if this is infinite, then it diverges to infinity. But if we actually get a finite value here for the limit of the partial sum, then we can say it converges to that value. So we bring back in our telescoping series, and we see that we had Sn equals 1 minus 1 over n plus 1. Now we can take the limit as n goes to infinity, but the only time that n appears is in the denominator. So remember, if we have 1 divided by infinity, that basically goes to 0. So we have a really small number divided by an increasingly large number. This is getting smaller and smaller overall, and eventually converges to 0, which means 1 minus 0 converges to 1. Okay? So the limit of S sub n is equal to, as n goes to infinity, it's 1 minus 1 over infinity, it's 1 minus 0, it goes to 1. Okay. Alright, because this one gets arbitrarily small, and we get to 0, and then 1 minus 0 goes to 1. So that means that for our telescoping series, it is possible to determine the sum. One of the things that we'll discover is that there's a lot of series that we ultimately will not be able to find the sum of. One, a lot of them go to infinity, but two, the pattern may be so complicated, there's no way for us to actually discover what that value is in a somewhat reasonable manner for the time that we have available. And some of them we just may not be able to find at all. The pattern is so complicated. And that's really what impacts it is this expression, this a sub n inside the summation. Depending on this level of complexity, we may or may not be able to do anything about it, or do anything with it. Next we will look at a geometric series. We did talk briefly about geometric sequence in section 9.1. This will be very similar, of course, but because it's a series, it means the terms are being added together. So the general pattern, and actually now the book agrees with me, it wants to start at n equals 0. The general pattern is the sum as n equals 0 to infinity of a times r to the n. Now, r is what we call the common ratio. And this is what we saw this in the sequences as well. It's whatever numbers multiplied to go from one term to the next. And that's why I call it the common ratio, because it'll be consistently applied from each term to the next throughout the series. And a is the first term of the series. Okay. For example, we might see a series such as this. 2 minus 1 plus 1/2 minus 1/4 plus 1/8. Let's just make it all pluses at this point. We'll start off positive. Okay. So 2 plus 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. So we can see our first term is 2. That's a. Now the question is, what do we multiply by to go from 2 to 1, from 1 to 1/2, from 1/2 to 1/4, and so on? Well, our common ratio is 1 over 2. Essentially, we can find r by dividing a1 over a0. Okay? Basically, taking this term divided by this term gives us the R value, because the same ratio should be true if we take A2 over A1, A3 over A2, and so on. So 1/2 divided by 1 is 1/2. 1 divided by 2 is 1/2, so on. And that will be true for every consecutive pair of terms in this series. So we have a value of 2 for A and 1/2 for R. That means our sum, n equals 0 to infinity, is equal to 2 times 1/2 to the n. Okay? Now, this pattern can be used to find any term of this particular series. And that's why we want to write it as a series in the first place, because if we need to know what the 100th term is, then we could we could figure these out and just keep going. Or we could just plug in n equals 100 and calculate this value. It's nice to have a closed form. We call this a closed form definition of the series, because now we can plug in a value of n and get the value of any number. This one is a more tedious process. Okay, now with geometric series, convergence and divergence is actually pretty easy. Convergence, this should be a C, sorry, and divergence of a geometric series. And this says it converges if the absolute value of R is less than 1, and diverges if the absolute value of R is greater than or equal to 1. And the concept is this: if our ratio is bigger than 1, if we keep multiplying by a number that's bigger than 1, the number is going to get bigger and bigger. Like, if we keep multiplying everything by 2, eventually our number is going to get larger and larger and grow without bounds, we would say. If it grows without bound, then it goes to infinity. That's the other word there. However, if we're multiplying by a number smaller than 1, such as 1/2 in this instance, the number is going to get smaller and smaller, and it becomes more manageable. We can actually add all those together, and we're able to determine the value of the sum in that case. Specifically, the sum is equal to A divided by 1 minus R. Okay. Not very often are we able to find the sum of a infinite series in a nice, easy formula, but this is about the only time we can. It's if it is geometric. Because it's completely based on the value of the first term and the value of the ratio, which is what we found in this case. We started with this list of terms being added together. We found the initial value and the common ratio. This continues throughout, and we're able to find a definition for the series in this case. 2 times 1/2 to the n. Now we can also find the sum based on this formula. So A is 2, R is 1/2, so 1 minus 1/2 is 1/2, and 2 divided by 1/2 is 2 times 2 over 1. which means we have a sum of 4. And what that means is that all of these numbers added together will equal 4. Let's look at that. We have 2 plus 1 is 3. 3 plus 1/2 is 3.5. Plus 1/4 makes 3.75. Plus 1/8 makes 3.875. Plus 1/16, which makes 3. Add 0.625. So 3.936 9325. I'm getting lost in the fractions. But the idea is that each step we take, starting from 2, gets us halfway closer to the sum 4. So after we get to 2, we're a distance of 2 from 4, we go half of that, 3. After we get to 3, we're 1 unit away from 4, we get half of that, 1/2. After we get to 3.5, we're 1/2 away from 4, we go half of that, 1/4. And so on. And so by that measure, we may think, well, we never actually get to 4 if we keep moving halfway closer each time. Every time we're moving towards 4, we cover half the remaining distance. And the idea is like, well, will we ever get to 4? Well, technically at infinity, yes, we get to 4. We don't really want to wait that long, though, it turns out. But for practical purposes, at a certain point, we're going to be so close to 4, it's going to be indistinguishable. Just whatever measure of accuracy we would like to use that to describe that, we're good with. When you look at a CNC machine, which machines using different materials, but usually with metal, different metal or metal alloys. Depends on what kind of machine you're working with. But I've seen some that also work with wood and other materials. Those are a little more specialized, I think. But anyway, a CNC machine, if you want to create, it's basically a 3D printer kind of, but it takes a block of metal. You start with your raw element, or whatever it is. It's usually, I forget the word for it. It's a block of metal, basically. And basically we carve out from there. We carve out the parts that we don't need, so we leave what we want remaining. And so it's different from a 3D printer in that sense, in that a 3D printer is more, it builds up the item from just laying down layers of plastic, and a CNC machine takes an existing block of material and slowly takes away what it doesn't want to get down to the element it does want, or the object it does want. But that aside, the point I'm trying to make here is that it doesn't have to be exactly perfect. So if we want a piece of metal that is a quarter inch thick, 2 inches long by 1 inch wide, it doesn't have to be exactly 1 inch wide. It'll be close enough that it's indistinguishable, so the machine doesn't have to have 100% accuracy. It just has to be close enough to do the job that it's designed for. So when we make a quarter inch screw, I mean, it just, as long as it's close enough, that's fine. It'll do its job. You compare them at the microscopic level, there's going to be some differences. Although with screws, they're usually made by the same machine, so that, and what happens is the parts wear out over time, and they have to be replaced. And the idea is that, okay, as that happens, there's going to be a little bit of difference, and once it drops to a certain point, then you have to replace the parts. Anyway, the point is that I'm finally going to get to it. things don't have to be perfect. They just have to be usable. They have to be close enough that we can use them for what they're designed for, and whatever we use it for works perfectly. So we don't have to have 100% accuracy in applications of math. It just has to be close enough. However we define close enough in a given situation. So we could make something that's exactly 1 inch wide, piece of material, piece of metal, or we could make it within 1 times 10 to the negative 6th accuracy of an inch, which is good enough because we're not going to be able to tell the difference. We could probably use calipers at that point and not know the difference. Okay, if we want a little bit more wiggle room, that's fine too. It just depends on what we need it for. I mean, if you're building a car part, then you want it to be reasonably accurate. It doesn't have to be perfect, but it has to be good enough to do its job and not fail immediately or within the first couple of years. If you're building a spaceship, if NASA's building a spaceship, or one of its contractors is building a spaceship to send into space, you're going to need a lot more accuracy because you have a much lower tolerance for failure and much more catastrophic outcomes of failure in that scenario. So they're going to be a little bit more precise in their construction and their calculations and so on. And that's really what it amounts to is when you get into engineering, it doesn't have to be perfect because what is the cost of perfection in that scenario? I mean, how much more does it cost to go from 4 places of decimal accuracy to 10 places of decimal accuracy, and can we save some money in that production? Okay, and then that becomes a more serious issue in the field of engineering that we don't really worry about in math. Because math, we like accuracy, we like to be as accurate as possible. But from a functional standpoint, can we get away with a little bit less? And that's overall the goal. Anyway, so this does get to 4, but after about 10 terms here, we're within a couple of decimal places accuracy. Okay, and so that's good enough. We won't be able to distinguish it from 4 if it's like 3.9996. Okay, that's close enough, depending on what we're doing. Alright, so even though things go to infinity, or as things go to infinity they finally reach a certain value, we can achieve almost the same level of accuracy if we only take like the first 10 or 12 terms. And actually that's what we see in our calculator a lot of the time, as far as how the calculator functions to give us the values when we punch in calculations. When we type in sine of pi, we know the value of sine pi is 0. But the calculator is using a formula to calculate this value that doesn't go to infinity, but as long as it goes far enough, it's going to give us that one value, because at that point it's indistinguishable. The concept of infinity is pretty weird. You can do some weird stuff for that. Alright. So that's geometric series, and geometric series is one of the only times we can actually find a sum of the series. Telescoping series is another such example that we looked at already. I don't know if there's any more that we look at where we can definitively find the sum. Okay. So, for example, if we have, let's look at another geometric series. 2 minus 8/3 plus 32 over 9 minus 128 over 27, so on. Sometimes we can recognize the ratio by looking at the expression. Other times we will have to actually divide the consecutive terms to determine what the ratio is. Now, from 2 to 8 over 3, it may not be as easy. If we think of it as 2 over 1, it makes a lot more sense to go from 2 to 8 and 1 to 3. It looks like we multiplied by 4 over 3. And we look here, same thing, times 4 over 3. 4 times 32 is 128, 9 times 3, 27. So the ratio is 4 over 3, and we can see it goes from minus to plus to minus, so our ratio is actually negative 4/3. And A is equal to 2 once again. Now, the question is, does this converge or diverge? Well, this starts out as 2. 8 over 3 is a number that's bigger than 2. That's like 2 2/3. 32 over 9 would be 3 5/9. And 128 over 27 would be 4 20 over 27. So these numbers are getting larger even though they're changing signs, plus minus plus minus. This is what we call an alternating series because the signs alternate from positive to negative to positive to negative. So it's a geometric series, but it's also an alternating geometric series. Okay, so alternating we define as any series where the signs switch from plus to minus continually. So this is an alternating geometric series, just to add on an adjective there. But our ratio is negative 4 over 3. Now, the absolute value of r is 4/3. Now, that's bigger than 1. Because our ratio, absolute value of our ratio is bigger than 1, go back to the previous page, we said if the ratio or the absolute value of the ratio is bigger than 1, the series diverges. Okay? And we can actually tell it's divergent because the numbers are getting larger and larger. Even though the signs are alternating, these individual numbers, just ignoring the signs, they're going to continue to get bigger and bigger. So we had 2, 2 2/3, 3 5/9, 4 20 over 27, and so on. So those numbers are getting larger very quickly. And because of that, that's why it actually goes to infinity, is because those numbers are growing bigger because we're multiplying by a number bigger than 1 each time. Okay. Next we have the Nth Term Test for a divergence. And this says the for a series sum n equals 0 to infinity of a sub n if the limit as n approaches infinity of a sub n is not equal to 0, then the series diverges. Now, in this case, we can only prove divergence using this Nth Term Test. That's why we call it the Nth Term Test for divergence specifically. And what we're saying is if the infinite if it was n goes to infinity, basically we get a number that's something besides 0. Now there's going to be a lot of series that have an nth term of 0, where if we get n equals infinity, we actually get a equal to 0. There's a lot of terms that both converge and diverge that will have a limit of 0. So that doesn't actually tell us anything if we get 0, but if we get a number other than 0, we absolutely know it diverges in that scenario. Because if we're adding together an infinite number of non-zero values, it's going to be pretty large, basically going to infinity. So part of that really determines on the formula for a sub n and how that works. And again, we may have to use, in some cases, L'Hopital's rule. That may be an issue. But most of the time, we're going to stick with just a normal limit, in this section at least. When we get to some of our more involved convergence tests, we might have to rely a lot more on L'Hopital's rule. The ratio test is all about L'Hopital's rule. So that's section 6. Okay. I'm wearing my headphones today to keep my ears warm. That's really the only reason. I'm not actually listening to anything here. Nor do I need to, because I don't usually when I teach, but my ears were cold, and this was a good solution, because they go over my ear, and it feels good. So. The problem with shutting the door to my room here that I'm teaching in doesn't allow the heat to circulate as well as you might hope into this room from the other rooms in the house. But my dog would certainly come in here and want to try to get attention while I'm teaching him. And don't really. I mean, that would be okay for a bit, but we don't need to make that a big deal. Anyway, it'll be interesting because I started teaching. I mean, we had the whole pandemic stuff hit in March last year, so it hasn't really been that cold when I've been teaching. So it'll be something I deal with, and you may see me wearing the headphones a little bit more. Anyway, so our nth term test. Let me find an example. I'm gonna look at some of the questions from the book now. It's not an example. This is problem 48 on page 605. We sum n equals 1 to infinity 4n plus 1 over 3n plus minus 1, sorry. Actually, it doesn't matter in this case. 4n plus 1 over 3n plus 1. So, we can try to apply the nth term test. It says we take the limit as n goes to infinity of 4n plus 1 over 3n plus 1. Now, in some cases we will have to use L'Hopital's rule, and this is one of them, because what happens is if we plug in n approaching infinity, we get an infinite number over an infinite number, which is indeterminate, as we call it. So, it was indeterminate, and this is like the pattern is infinity over infinity or 0 over 0. We can use L'Hopital's rule. Okay, so we have a limit as n goes to infinity. Now, the way L'Hopital's rule works, and I feel like we've used this fairly recently, but just to refresh, if we get infinity over infinity or 0 over 0, we can take the derivative of the top and the bottom of this fraction independently. That means we take the derivative of 4n plus 1, which is 4. We can take the derivative of 3n minus 1. I wrote it wrong the second time. But again, derivative of negative 1 is 0. The derivative of 3n minus 1 is 3, and so we end up with 4/3. And now we take the limit as n goes to infinity. Now, in this case, n is going to infinity, but we don't have any n's left in our expression, so it's just equal to itself, 4/3. Now, its limit is 4/3, which is not equal to 0. Therefore, it diverges by the nth term test. Okay. All right. I don't know what to deal with my webcam is. It's a little cold, I guess. I don't know. It gets stuck sometimes. I just hope I'm not making a goofy face when it happens. It does happen. Alright. Let's look at 52. Let's see, we have sum n equals 0 to infinity of 7 over 5 to the n. Now we look at this and we might think, well, let's try the nth term test. We don't have a lot that's available to us right now, but let's try nth term. So we take our limit as n goes to infinity of 7 over 5 to the n. Now 7, there's no n up here, so we'll just make 7. But 5 to infinity power is equal to infinity. Okay. In fact, let me add this note now. A to the infinity goes to infinity if absolute value of a is greater than 1 and a to the infinity goes to 0 if absolute value of a is less than 1. If it's equal to 1, it's indeterminate, actually. Because 1 to infinity is one of our indeterminate forms. Anyway, so 5 to the infinity, 5 is bigger than 1, so that's going to go to infinity. 7 over infinity goes to 0. Okay, any finite number divided by infinity is always 0. One of the most abstract things we have to be able to deal with here is just working with infinity and how it interacts with other numbers. Now, infinity is so large it usually wins any fight. It just determines which side of the fight it's on, the numerator or the denominator. If it's in the denominator, it goes to 0. If it's in the numerator, it goes to infinity. That's really what it amounts to. Okay, so this is 0. Now, nth term test doesn't tell us anything if the limit is 0. Okay, so the nth term test is inconclusive in this case. So what that leaves us really is geometric series. And this, while this may not look like our traditional geometric series, it is actually geometric. Let me have to go to the next page, however. Now you might say, well, it's 5 to the n in the denominator. How is that geometric? Well, let's think about it like this. It doesn't really fit our pattern of a times r to the n. Okay, it doesn't really fit that right now. So we factor the 7 out, so we have 1 over 5 to the n. And 1 can be written as 1 to the infinity power. Well, not infinity, that's indeterminate as we said, but 1 to the n is still going to equal 1. It's a little weird how we follow these rules sometimes. Basically, we said 1 to the n is basically 1, or it is equal to 1. And because now we have an n on both of these terms, we can think of it as 1/5 to the nth power. Okay. Now it looks like our geometric series. And what's more, we can say r is equal to 1/5. And it's less than 1, so it converges. Okay. The ratio, the absolute value of the ratio is less than 1, so it converges. And in this case, for a geometric series, because it converges, that means we can also find the sum of the series. Sum is equal to a over 1 minus r. In this case, a is 7, and r is 1/5. So 7 divided by 4/5, which is 7 times 5 over 4. So the sum of this series will be 35 over 4. Okay. I think my webcam is just checked out for the day. Okay. Alright, so that's our geometric series. And we looked at Nth Term Test. Nth Term Test is interesting, but again, it can only be used to solve or to show divergence in those cases. And don't worry too much about telescoping series. I went ahead and mentioned that, but I'm not going to actually test you on telescoping. The other ones I would consider eligible for testing, nth term and geometric, but not telescoping. It's rather specialized, I would say. One other topic we want to look at this, and it may not initially seem connected to series at all, but that's the concept of a repeating decimal. And the idea is we want to find a fractional representation for a repeating decimal using series. Now when you say repeating decimal, it might be that we have 1, 2, 1, 2, 1, 2 repeating. And sometimes you see it written as 0.12 with a bar over the 1, 2 to show that this is the repeating pattern. Okay, so let's look at how we could use a series, especially specifically geometric series, to determine what that's equal to. First thing that we'll do is I'm going to split that up into multiple parts. So I'll make it 0.12 plus 0.0012 So basically take these three parts here that we're looking at and write them as separate decimals. Okay? So we have our first 0.12, and then we have our 12 that follows, which would have 2 zeros in front of it. To add those together and equal 12. This one has 4 zeros in front of it, and then 12, so that we can add all three of these to get 12. Okay. And then we would continue that pattern from there. Now, all we have to know is that it's continuing. We don't really have to keep going, basically. What we're going to find now is that if we look at this is now a series where we had an infinite decimal, so we've turned it into a series, and we just have to figure out the definition of the series now. And it turns out to be geometric, because we have our first term, a, is 0.12, or we can think of it as 12 over 100. We could reduce that. It might be easier if we don't reduce it. Just, we'll see. And then we need a common ratio. How do we get from 0.12 to 0.0012? We multiply by 0.01. And same thing's true here, times 0.01. And we can, if in this one, we might want to verify on the calculator. And again, the way that we test this out is we can take the second term divided by the first term, and it should equal our common ratio. This term divided by this term should equal the common ratio. So if we took 0.0012 and divided by 0.12, we get 0.01. If we took 0.000012 and divided by 0.0012, it gives us 0.01. Okay? So in both cases, we found a ratio, or multiplier of 0.01. So that means R is 0.01, which more accurately is 1 over 100. Alright. So our sum is A over 1 minus R. So that's 12 over 100 over 1 minus 1 over 100. Now, 1 we can think of as 100 over 100 minus 1 over 100, which gives us 99 over 100 in the denominator. Now, with this division of these two fractions, since they both have the same denominator, it's going to cancel out. So we're going to get 12 over 99. So our sum is 12 over 99, and we would reduce it from there. Luckily, I have a function on the calculator that reduces fractions for me. 4 over 33. I mean, we could figure that out. That was divided by 3, but if it goes further, it's kind of nice to have. Now, 4 divided by 33, just to double check. You see this 0.121212 repeating. So it does fit the pattern that we are working with. And you might say, well, anytime we have a 2-digit repeating decimal, it's just that number over 99. And that's true. So if we had 0.36363636 repeating, then that would just be 36 over 99. And that's correct. Whoops. There you go. And if we had 45 over 99, that should be 0.45 repeating. And we see that's true. 72 over 99. 72 repeating. Okay. It actually applies to three decimal repetitions as well. So if we had, 0.123 repeating, like so, that would be 123 divided by 999. Now where it gets a little bit more difficult is, it's not that much more difficult, but it does require a little more work, is if we have part of the number, let's say we have like 0.5 and then 43, 43, 43, 43. It's like we have some number that's not connected to the repetition, but then it continues to repeat after that. So 0.5 is kind of separate, and then 43, 43, 43, we get that repetition. It's still an infinite decimal. It's still valid. But let's look at that example. So, we're going to take our 0.5, and we're just going to separate these terms the same way, but we'll also separate the 0.5 since it's not connected to the pattern. And we'll have 0.043, 043, and then 00043 for the next one, plus there's 1, that was 3, so now we'll have 5 zeros, and then 43. Okay, and it just continues from there. Now, 0.5, we know that's 1/2, and this is 43 over 1,000, and this is 43 over 100,000, and this is 43 over 10 million. And so on. And what we see, we're multiplying by here, our ratio. So there's A, and our ratio, we're multiplied by 100 on the denominator, because we're adding 2 zeros each time. So 3 zeros, 5 zeros, 7 zeros. So it's 1 over 100. Anytime we have 2 number repetition, like we saw here in the problem above, it's 1 over 100. Okay. 3-digit repetition, like if we have 1, 2, 3, 1, 2, 3, 1, 2, 3, it'd be 1 over 1,000. Okay. So our sum is going to be 1/2 plus a over 1 minus r. So when we create our sum, we don't want to forget the extra 1/2 that we had at the beginning, plus what's actually forming our infinite series, which is the rest of the pattern. A we said was 43 over 1,000 over 1 minus 1 over 100. So you get 1/2. And this would be 43 over 1,000 over 99 over 100. That's a little bit tougher. So we'll probably want to go ahead and work a little harder on that one, I guess. So 1/2, let's see, so this is 43 over 1,000, and it's divided by 99 over 100, so times 100 over 99. Now 43 is prime, it's not going to reduce to anything, but 100 over 1,000, we just leave a 10 on the bottom. So there'll be 1/2 plus 43 over 990. Okay. I'm just going to go ahead and put that into my calculator. 1/2 plus 43 over 990. Oh, I did that by accident. Okay. We know it's correct now. Well, I don't know why we wouldn't have suspected that. 269 over 495. Okay. And if we actually divide those, 269 divided by 495, 5. And we see our pattern emerge, 0.53, or sorry, 543434343. Okay. I don't know how much value there is to be able to do that. It's nice to be able to know when we have what pattern we have when we have a repeated decimal. It turns out any repeated decimal can be expressed as a rational or as a fraction. Okay. Specifically, a fraction that is a ratio of two whole numbers, which is kind of neat, I think. But the more complicated the repetition, the more complicated the fraction that actually represents that is. And this one is already kind of difficult. It's not like a nice fraction. It doesn't reduce or anything like that. But yeah. All right. That wraps up 9.2, and I said last time we would just cover 9.2 on its own as we kind of ramp up things in this chapter. There's a lot here. I didn't want to dive into it too quickly. That way you have time to digest the material. So I'm going to stop there, basically. Long story short. For homework, this is page 605. Let's see. Go ahead and look at number 11. $13, 15, 29, 33, 43, 45, 45, 47. And go ahead and give 49 a try also. Hmm. 57 is also fun. I don't know if you'll... It's not strictly necessary that we do that one, but I think it's interesting. So we'll leave it at that. So you'll have a good rest of the day. Stay warm. And we will continue on Thursday with Section 3. So take care, and I'll see you then. Bye.